Hello, assalamu alaikum everyone. I hope you guys are enjoying your preparatory leave. Today, I thought I should be giving you a lecture on solving an aeroelastic numerical problem from Megson's book. And this is a rather very simple problem and it's very easy to solve it. However, I found it could be very difficult for you to understand some terminologies because we did not go through that maybe in the class, because I thought you may have covered this in your previous lectures and previous courses from aerodynamics or aircraft performance. However, I don't want to take any risks for your exam, so I'm going to make this video so that you can understand how to solve this problem. So this is a divergence problem. For a divergence problem, you have to understand this is a static problem, and we will not cover how to derive the problem. However, what we're going to do is we may discuss some terminology while solving this problem, and yeah, let's move on to the problem. So the given problem is an aircraft has an area of 330 meters square and an aerodynamic mean chord of 3 meter. If the aerodynamic center of the wing is 1/4 of the wing chord forward of its flexural center. This flexural center, we did not discuss that in the class maybe. So if you can remember, we have three different center. We'll show you once again after a few minutes. But flexural center is basically the elastic axis or elastic center or twist center, whatever you call it. Different book gave it a different name. In Megson's book, they call it the flexural center. In some book, in some videos in online, you can find they call it the twist center. Sometimes they call it the elastic axis. Its lift curve slope is 3.5 and the design diving speed of the aircraft at sea level is 200 meters per second. Now calculate the minimum required torsional stiffness of the wing. So what is design diving speed? This term is very new for us maybe, because I'm not sure like if you have done it in your aerodynamic class or not. Basically, design diving speed is the maximum speed or top speed or highest speed that is planned for an aircraft to be achieved. Beyond that, we should not fly. Now, the assumption has to be made this is a two-dimensional flow. We're not considering 3D problem because 3D problem is much difficult. If you go further into aeroelasticity, you may have to consider three-dimensional problems. But for our course, because it's a subsection of a larger course, so we have confined ourselves within the two-dimensional flow, right? Now let's extract the data first. For example, these are the given: mean aerodynamic chord, area, slope, diving speed, air density, and this statement is given. Like our aerodynamic center is quarter chord forward of flexural center. Now refresh our memories from the offline class. Right section here you can see is the wing, one section of the wing. I have to remind you, like this is a static problem, and even though we have aerodynamic center, we have elastic axis, which is also known as flexural center in this particular problem. And if the terminology is different, then you should not be worried. Elastic axis and flexural center is the same place, at least for this problem. Okay. And we have inertial axis. So this inertial axis is only for when we're calculating the flutter or any kind of dynamic problem. In that case, we'll consider the inertial axis. But for this particular case, we'll be just confined ourselves with the aerodynamic center and elastic center. Let me draw some in here. The distance from here to here is the one chord length, right? I hope you understand that. Okay. So this is the cross section of the aerofoil, and we are assuming two axes. Why? Because it's a static problem, so we will only consider the elastic axis and the aerodynamic center, or in this case we are calling it the flexural center, and the distance between these two things is called EC. So here we can see there's a chord, the yellow line, the chord length, and in our case it's given 3 meter, right? 3 meter is given. Okay. And there's another term which is called quarter chord. Quarter chord means 1/4 times the chord length. So what does quarter chord mean? For example, we have this chord, right? From here to here we have a length of C, or 3 meter for here, for example. So if you can count, like we have 10 sections, 1 2 3 4 5 6 7 8 9 10, with 10 sections here. Here we want to move forward 2.25, like this. For example, this is one section, two section, half section. So this is like 0.25 of chord, right? So from here, if our aerodynamic center is 0.25 forward of elastic axis, that means we have to move forward from here 1 2 and half. So this distance, again, I'm giving a disclaimer here. This is not the actual scenario, maybe because the elastic axis, maybe it's here, here, or maybe here. We are just assuming, to simplify the problem, that our elastic axis is here and we're moving quarter chord, because it's given, forward to find the aerodynamic center. Okay, I hope you understood this term. The aerodynamic center of the wing is one quarter chord flexural center. That means I have to go quarter chord forward from this distance horizontally. Okay, now we know that it's a beautiful problem and beautiful equation. We solved it in the class, where K is the torsion, rho is the density of the air, S is the area of the wing, EC is the dimensional elastic margin, which is also known as the distance between AC and EA, and this A is what? This term, lift slope curve, right? Okay, so these are the given data. We just squared the whole equation. Why is that? Because we're interested to find this K, torsional stiffness. After squaring it, we get this one, and after rearranging it, we get this beautiful value, and then this equation is achieved. This is the torsional stiffness of the designed wing. Okay, now plug those values. For example, the divergence speed is given, like diving speed is given 200, as you can see from this given data. Then we have rho, which is 1.266. Okay, here it's given. Then this is the wing area, which is 30. EC, that means 2.5 times the chord length. The chord length is 3 meter, and we have the lift slope curve 3.5. Apply these values, you get this beautiful answer, 1.39 into 10 to the power 6 Newton meter squared. So this is a very simple problem. Maybe during the exam I will change something, or maybe you have to use your rational to solve this problem. Maybe I can increase those length of the question. For example, I may ask you, if the wingspan, I designed this one, right? If the wingspan is increased 3 times, what will be the divergence speed? Or maybe if I change the torsion after calculating all those, or if I change the lift slope curve, or if I move the EC, the distance between AC and EA, further or closer, what will be the divergence problem? So this kind of tricky questions may come in the exam, but follow this procedure. First, you need to know the equation. You write down the equation, then extract those data and understand the question properly, and then answer it. Because what happens in most of the cases that we do not understand the question, we just write very hastily, because if you see some problem and the numerical values are the same, we start write down like in supersonic speed. We do it very slowly, calm, and we get these values. I hope you understood the problem. If you have any question, you can ask me on the WhatsApp, or you can write it down on the comment section. Thank you.